So in a previous lecture, we looked at how do you compute the voltage, equilibrium voltage of lithium-ion battery, and then how, as a function of different approaches to exchange correlation function, how does the voltage change? Okay, so we will move on. The next particular property that is important in understanding lithium-ion batteries computationally are the voltage profiles. Like how does, as the battery is getting discharged, how does the voltage change? So we know, we in the previous lecture, we talked about the reaction or that we are considering. Once that is clear, we can compute the energetics using density functional theory, and a simple formula exists how to connect this energetics to voltages. So what makes voltage profile more complicated? Okay, so we won't be able to do much of this because lots of issues are connected with how do you incorporate the effect of temperature. How to incorporate the effects of temperature within DFT. Okay. Within quantum mechanics or within DFT. This is all what comes under the domain of quantum statistical mechanics. See, what does statistical mechanics or statistical thermodynamics tries to do? You start from molecular properties and connect it to derive the macroscopic thermodynamic properties. Macroscopic thermodynamic properties, right? So that's what is being done in this case. It can be classical. Classically, you can compute molecular properties and connect it to macroscopic properties. In this case, we are interested in quantum statistical mechanics in the sense that you use some methods like DFT and then do molecular calculation connected to macroscopic thermodynamic properties. Okay. To incorporate temperature, we need thermodynamics. If you look at the fundamental equations of classical mechanics and quantum mechanics, there's no temperature. Okay, so in neutron stars doesn't have temperature. Schrodinger equation doesn't have temperature. So you have to go to statistical mechanics to incorporate temperature, and how do you connect them is a different topic, a different class altogether. So an approach that has been fairly successful is what is called cluster expansion approach. I would strongly advise someone to take up this thing. I will approach some students to take up this topic for the term project. Okay, cluster expansion. So this is an important approach to computing the voltage profile. Okay, so here on the paper also, there is it's an example that has been dealt, and I will just bring out some features of the paper. Okay, so the paper of the figure, we won't go elaborate a lot into this because so that will this cluster expansion itself will take few lectures, which I don't think we have available with us right now. Okay. Okay. So what is that? What is the issue? What is the complication? Okay. So the complication is in all these simulations, is in obtaining the structure. When lithium intercalates, structure of the cathode upon lithium intercalation, or in the case of intercalation, or in the case of conversion electrodes also, okay? What is the structure of the conversion electrode, okay? So what is that we're talking about? When lithium binds to the cathode, there can be more than one possibility for the structure. It can first bind at different binding sites. There can be vacancies that are created. With respect to each other, the vacancy can be ordered in different ways. There can be certain phase transitions that can occur. So there are lots of issues here, okay? So there can be phase transitions. We look at these issues a lot in our group. Phase transitions, lithium ion vacancy ordering. Okay. So the lithium ion, different lithium ions or different vacancies that are created can interact with each other, and certain configurations are lesser in energy compared to certain other configurations. So when we are talking about lithium binding to the cathode, even at a particular composition, we are not talking about one particular structure. There can be a variety of structures that have to be computed and incorporated into the calculation. So for example, in this picture, so what we are trying to do is for a particular composition, okay, let's take 0.33. There are different calculations, okay, corresponding to different structures. The energies of different structure, formation energy, which is indicative of the voltage that can be generated, is also different. So how we have to have a way of sampling these different structures and computing their energetics. So that's where this cluster expansion technique becomes important. That originated in physical metallurgy. If you have a metallic alloy, how do you think about the structure of the metallic alloy? Okay, that was reason why cluster expansion approach was initially generated in materials. I mean, it was utilized in material science. That was later translated into computational understanding of cathodes. Okay, so what you try to do is you calculate different structures and the energetics corresponding to different structures, and then the lowest structure, this is called the convex hull. Okay, so the lowest structure, the lowest energy amongst all these structures is what is most significant for you. Okay, so at 0 Kelvin, only the lowest energy can be accessed. Okay, the higher energy structures cannot be accessed. So with such, so you calculate the energetics at different x's, okay, a different state of a charge, and then calculate the potential. And here there's a comparison between the calculated potentials and experimental potentials. Okay, so as you see, what is nice about DFT, usually you get correct trends. Okay, so that's where for many engineering purpose, correct trends is always important. Okay, so even though there is some difference between the experimental and first the experiments are smooth. Okay, so here it's jagged. Okay, because of we are considering a homogeneous structure. Okay, we're considering only one structure and not excited structures and so on. So as the temperature, so most of the time we are computing we are making a 0 Kelvin calculation. So only the lowest energy structures are accessible. Okay, so at higher temperature, there are methods to incorporate finite temperature. One is using some simple classical statistical mechanics tools we can incorporate. We talked about this Boltzmann occupation and so on in the previous lecture. There are more advanced methods. We can use what is called ab initio molecular dynamics. Maybe I will give a lecture at a later stage on this. There is something called Monte Carlo simulations, okay, Metropolis Monte Carlo simulations, which we may not go to, but I would give a lecture on AMD. Okay, so that helps you incorporate these issues of higher temperatures. Okay, so when you also include the effects of temperature, the comparison becomes better. Okay, so this is not exactly a battery material, but the physics of the problem is very relevant. The methods that we are using for looking at this system is very, very relevant to what we do in batteries. Okay, so this is so what I request. Okay, so this is an important approach. Okay, so if you want to get cathode modeling right, you have to have a good handle on this cluster expansion technique. Okay, so as I said, you can take different projects. The projects can be on catalysis, it can be on batteries, and it can be on separation systems and electronics, mechanical properties, and so on. So, but if you want to, I would strongly urge at least one student. I have some students in mind. So I want you to strongly urge you to take a look at cluster expansion technique for understanding how to incorporate statistical mechanics into the modeling effort. And that's going to be important for understanding these kinds of systems. So with that, that's what I want to say about voltage profile. I don't want to go into additional details at this point of time. It's stuck.